All right, guys, so what in the world is a rational function? A rational function, guys, is any function containing a fraction or fractions with a variable or variables in the denominator. I'm abbreviating here, guys, okay? So any function containing a fraction with variables in the denominator or with a variable in the denominator. So when we look at the rational function, guys, one of the most common rational functions you will encounter is f of x equals to 1 over x. Now, because this is a fraction with a variable in the denominator, that variable is open to any value. So the question you have to ask yourself is, what value should we exclude from the denominator of this fraction, okay? What value can't the denominator of a fraction be? Remember, the denominator of a fraction, guys, cannot equal to 0. So for these problems, you have to be careful, guys. You want to restrict or exclude any values from the domain of this function that would make the denominator equal out to 0. You want to restrict or exclude any values that would make the denominator equal out to 0. And how do you find them? What you do is you set the denominator equal to 0 and solve, okay? So this will give you the restricted or excluded values, such as the case with this problem right here. We know, guys, x cannot equal to 0 because if x is equal to 0, what happens? The denominator becomes 0. You can't divide by 0, so this would be undefined. So which means when we graph this function, guys, this function will not be defined at 0 at all. So when we write out the domain for this particular function, the function is defined everywhere else except at 0. So when you write it out, you're going to have an interval from -infinity up to 0. 0 is not included. And then union from 0 not included up to +infinity. The function is defined for every single x value except 0. Okay? So guys, that is the first step with these rational function. You got to find the excluded or the restricted value or values in the domain of these functions. And to find those restricted values or excluded values in the domain, you set the denominator equal to 0 and solve. Set the denominator equal to 0 and solve, guys. All right? So that's the first step, guys. So let me go ahead and run through a few example problems. And for these, when you see them on the assignment, guys, they're simply going to ask you to find a restricted value. They're not asking you to write the domain and interval notation. So here's an example. For this one right here, we're looking for the restricted value. What value makes the denominator 0? What number -3 makes the denominator 0? That value would be, yes, +3. So that means that x cannot equal to +3. So this function is defined for every single x value except +3. Yeah, that's it. You don't need to write out the domain. They're not asking for the domain. They're just asking for the restriction in the domain. That's it. So guys, here's the next one. F of x is equal to x minus 1 over x squared minus 4. Now this one is a little bit more complicated, so be careful with it. I am actually going to take the denominator, set it equal to 0 and solve it. How do I solve it? I'm going to factor x minus 2, x plus 2. So this one will have two values that will make it equal out to 0. X cannot equal to 2, x cannot equal to -2. As in, what number -2 makes the parentheses 0? +2. What number plus 2 makes the second parentheses 0? -2. So this one has two restricted values. Now guys, not all rational functions have restrictions on the domain. Some of them have no restrictions on the domain. Here's an example. F of x is equal to 2 over x squared plus 1. For this one right here, guys, remember, the restricted value makes the denominator 0. So can you find a value such that when you square it, add it to 1, that would make this equal out to 0? It is impossible. And if you were to attempt to solve this, you would subtract 1 from both sides. Notice I'm not factoring it, guys, because it's not factorable. You take the square root of both sides. What do you get? You get some imaginary values. How in the world are you going to graph imaginary values? You can't. So this one, guys, has no restrictions. So this one, when they ask you for the domain, you would say the domain is all reals. Okay, the domain is all reals. Okay, so on this one right here, guys, be careful. There's no restrictions on the domain. All right, here comes part 2, guys. Part 2, we are going to now find the asymptotes. Okay, find the asymptotes. Find the asymptotes. Notice I said find the, oops, wrong ass. Okay, find the asymptotes. I always do that for some reason. Now, the asymptotes, guys, there are 3 of them. In this particular class, I'm only analyzing 2 of them. There is a vertical, by the way, let me go back a little bit. What is an asymptote? An asymptote is an imaginary line, okay? A line which, or a value, you could also say a value, a line which a function approaches but will never get to. It's like a wall in the graph, guys. Approaches but will never get to. Why? Because it's undefined at that value, okay? So guys, when we talk about the asymptotes, all of them, they're going to be an equation. And so be careful, guys. When you are on the assignment, they will ask you for an equation because these are lines, okay? So there's 3 asymptotes. There's a vertical asymptote, which we're going to talk about first. There's a horizontal asymptote, a horizontal line. And then there's a third one, which I am not going to emphasize in this class because I'm going to save that for pre-calculus, okay? And that is the oblique asymptote or the slanted asymptote, which is basically, guys, a diagonal line. Yeah, so there's 3 asymptotes we look at: vertical, horizontal, oblique, or slanted. We're not going to discuss this one. When I come to a problem that involves an oblique asymptote, I will mention it, but you don't have to worry about finding any of these on the assignment. Okay, guys? So let's go ahead and talk about how we find the vertical asymptotes first. The vertical asymptotes, guys, vertical asymptotes. Basically, they are the restricted or excluded values in the graph. That's how you find them. So pretty much you set the denominator equal to 0 and solve. Now, this is going to be an equation, guys. The equation will be in the form of x equals to some value. Once again, it is going to be an equation in the form of x equals to some value. When you write the equation of the vertical asymptote, it must be x equals 2. If it's not x equals 2, the computer will mark it wrong, guys, okay? So here are some examples. The first problem I did with you was f of x is equal to 1 over x. And by the way, when I go on the graph with you guys, on the graphing calculator with you guys, I'll show you those vertical asymptotes I'm talking about. If you guys have your graphing calculators in your possessions, you can actually type these into your graphing calculator by going to the Y editing screen, Y equal to, and typing 1 divided by x and hitting graph. What you will notice is that this graph right here is undefined at 0. So when you sketch the graph, guys, the graph will look something like this. So it's defined in this region right here, and it's also defined in this region over here. And that is because this graph is undefined at x equals to 0. So this graph has 2 regions where it is defined. From negative infinity up 2, 0, but not including the 0. And then over here, guys, in the first quadrant, from 0 not included up to positive infinity. So the vertical asymptote, so the vertical asymptote for this one would be the restricted value. And what's the restricted value? X equals to 0. So that's the equation for it. And that's it, guys. Okay, let me do another one. Now, this next one right here is f of x is equal to x over x minus 3. Just ask the question, what is the restricted value for this one? The restricted value is 3. So then this becomes your vertical asymptote as well, x equals to 3. So the graph gets closer and closer to x equals to 3 on both sides, on the left side and the right side, but we'll never get to x equals to 3 because it's undefined at x equals to 3. So guys, if you go ahead and graph this one, x equals to 3, let's say it's right here, there's your vertical asymptote. So the graph would sit up here somewhere. By the way, there's something else I'm supposed to pay attention to, but I'll mention it in a little bit. And then you've got the other part of the graph over here, guys, okay? Yeah, so the graph will never get to x equals to 3. So that's number 2, everybody. Now, here comes number 3. Number 3, I've got f of x is equal to 2 over x squared. Now, we saw this one earlier, and remember I told you guys, there was no restrictions on the domain of this one. Since there's no restrictions on the domain of this one, therefore, this one right here has no vertical asymptote. No vertical asymptote. No vertical asymptote, guys. So when you graph this one, you're not going to find any breaks on the graph. There's not going to be any pawns. This is going to be a continuous graph, guys. So in other words, you can graph it without lifting your pencil, a continuous graph. All right, now, here comes the 4th example. Now be careful with this one. This one is f of x is equal to x minus 2 over x squared minus 4. Now, this is a special case, guys, special case. All right, first and foremost, what values make the denominator equal to 0? That would be x equals to 2, x equals to negative 2. And these would represent your vertical asymptote. But guys, wait, hold up a minute. I want you to notice something here. If I were to factor the denominator of this fraction, it would be x minus 2, x plus 2. And then, guys, I would be able to simplify out the x minus 2. So this problem would simplify to 1 over x plus 2. It's still the same problem, but we're simplifying it, guys. So by simplifying this to 1 over x plus 2, we no longer have 2 vertical asymptotes, x equals to 2, x equals to negative 2. We only have 1, x equals to negative 2. So when you graph this, guys, the only asymptote you're going to see on this one is x equals to negative 2. And then some of you will ask, well, what happens with the x equals to 2? The x equals to 2 was originally a vertical asymptote, but because we remove the vertical asymptote, we call this a removable asymptote or a removable point of discontinuity. We removed it. And because we removed it, guys, it's no longer a vertical asymptote in the graph. It becomes what we call a hole in the graph, guys. So essentially you're graphing this, you get to x equals to 2. At x equals to 2, the graph is undefined, but it's not going to be a vertical asymptote. It's just going to be a hole in the function. It's really hard for you to see a hole in these graphs on the graphing calculator. You just have to go to the table and notice, guys, on the table, there's an error message at x equals to 2. By the way, for those of you with the graphing calculators, if you graph a function like this on the graphing calculator tips, guys, if you're graphing this on the graphing calculator, look, guys, you have to enclose the numerator inside a set of parentheses, then divided by the denominator enclosed inside a set of parentheses. You would hit graph, you will notice the vertical asymptote at x equals to -2. But to verify there is a vertical asymptote at x equals to -2, and there are restricted values on this function, go to the table, guys. Hit second table, second, and then hit table, and the table will pop up. And on the table, it will say an error message at -2, error message at +2. Those two are the restricted values, okay, which are supposed to represent the vertical asymptote. So you can use the graphing calculator, guys, to help you figure out your restricted values and your vertical asymptotes. All right. So I'm going to pause on this one right here, and I'm going to switch over now to the horizontal asymptotes. Guys, remember, ultimately, our goal is to graph these functions. So we're taking it component by component, each characteristic one at a time, and then we're going to bring it all together to graph a rational function, okay? At least one, all right? So the horizontal asymptote, guys, is next. What is a horizontal asymptote? Just like a vertical asymptote, this is a line the function approaches but will never get to. Now, the horizontal asymptote is an equation. It has to be in the form of y equals to some value because it's a horizontal line. When they ask for the horizontal asymptote, if you don't type it in as an equation, guys, the computer will mark it wrong. Now, when it comes to the horizontal asymptote, there are three things we'll look at. There are three cases for the horizontal asymptote. So guys, pay careful attention to this. And of course, you can always go back over the video, okay? So how do you determine the horizontal asymptote? There are, basically it has to do with the degree, okay? You look at the degree. The degree in the numerator, which I'm gonna refer to as n, and you compare it with the degree in the denominator, guys. So what determines the horizontal asymptote? This is only for horizontal asymptote, guys. Okay? You look at the degree in the numerator and compare it with the degree in the denominator. And there are three cases to this, guys. So case number one says, if the degree in the numerator, degree of the numerator, is less than degree of the denominator, or the degree in the denominator, the horizontal asymptote for this one is automatically going to be y equals to 0. Automatically, y equals to 0. As long as the degree in the numerator is less than the degree in the denominator, automatically the horizontal asymptote is 0. Y equals to 0. And you have to have an equation, guys, okay? So what in the world am I talking about? Here's an example, guys. F of x, remember this from earlier, is equal to 1 over x. So remember, guys, the degree has to do with the powers, okay? In the numerator, there's no variable in the numerator, so the degree is 0. In the denominator, we got the variable x in the denominator. So in the denominator, guys, the degree is going to be 1. So what do you notice? The numerator is 0, the denominator is 1. So the horizontal asymptote is going to be 0. So
I don't understand.
Okay.
Why is 1 0 and why is x 1? Why
Okay.
aren't they both 1?
No, they're not both 1 because the power, when you have an x variable with no power, the power is understood to be 1.
So
Okay?
wouldn't that be the same with the 1 too?
No, because in the numerator, in order to get 1, you have to have a variable raised to 0 power. Anything raised to 0 power is equal to 1. Yeah, so it's the 0 power that would give you that 1. And if you were to put a 1 times x to the 0 power, it's the same thing. Okay, so pretty much if you have a number or constant, the degree involves the variable. Since there's no variable there, it's automatically 0. Does that make sense? Anyways, Jennifer, if the x equals, the x variable has a degree of 1, why would 1 also have a degree of 1? Seriously, think about that. Oh, wait a minute. I didn't mean to erase all of that, guys. Okay. So if the denominator has a variable x and its power is 1, how can the numerator that doesn't have a variable x also be a power of 1? It can't be a power of 1. That wouldn't make sense. All right? So anyways, guys, let me go ahead and carry on. It will hit you later, Jennifer. You'll come back to this and say, oh, okay, now I get this.
Can I ask one question?
Yes, absolutely.
So if it was a 2, it would still, if the top number was a 2 instead of a 1, it would still be to the power of 0?
Yes, absolutely. As long as you have a number there, the power is going to be 0 because there's no variable. And remember, you can take any number multiplied by x to the 0. Why? Because x to the 0 is equal to 1, so you still get the same number right back. Yeah. All right, guys. So let me go ahead and finish this up. I keep erasing this. That's not what I mean to do. Okay, guys. So let's go back to the fact that the graph of this, guys, has a vertical asymptote at x equals to, x equals to 0. And now it's got a horizontal asymptote at y equals to 0. So when you graph this, guys, the graph shows up in the first quadrant and then the third quadrant. That's why the graph looks like this. I know some of you were wondering earlier, why is this graph sitting above the x-axis? Why is it sitting below the x-axis? That was because of the horizontal asymptote. Not only does it have a vertical asymptote, guys, at x equals to 0, vertical asymptote at x equals to 0, that number that makes the denominator equal out to 0. It also has a horizontal asymptote at y equals to 0. So that's why you see the graph above the x-axis, below the x-axis, but never intersecting the x-axis. All right. Now, guys, here comes the next one. Okay, for this one right here, I'm going to look at f of x is equal to 2 over x squared plus 1. Now, for this one right here, guys, listen. The numerator, Sean, this was your question. The numerator just has a value, okay? So the degree is going to be 0. But the denominator, the power on the variable is 2. So the degree in the denominator is 2. So as you can tell, the degree in the numerator is less than the degree in the denominator. So automatically the horizontal asymptote is going to be at 0. When you sketch the graph of this one, guys, it is simply going to be a graph that looks like this. You've got a horizontal asymptote at y equals to 0. So the graph is going to look something like this. It will never intersect the x-axis, something like that. Yeah. Okay. You can throw this on your graphing calculator, by the way. If you're plugging this into your graphing calculator, guys, you do 2. Here, let me write it down for you. 2 divided by, open parentheses, x squared plus 1. You know, you go to your y editing screen, hit y equals 2, and type it into your graphing calculator, hit graph, and this is what the graph will look like. Yep.
I'm still stuck on the exponent thing because when I put 2 to the 0 in my calculator, it gives me the answer 1.
Yes, but this is not 2 to the 0, okay? This is, remember, the degree has to do with the power on the variable. There's no variable there, so you can always substitute x to the 0. Because x to the 0, like you just said, I raised 2 to the 0 power, that's going to give me 1. So any variable raised to the 0 power is going to give you 1. So if you take that 1, you multiply it by 2, that gives you a 2 back. Remember, the degree has to do with the power on the variable. Not on the number, on the variable. There's no variable there, x to the 0.
Okay.
All right. So guys, that was the second example. I'm going to move on to the second case of horizontal asymptote. Now, remember, horizontal asymptote has to do with the degree in the numerator and the degree in the denominator. So here's the second case. When the degree in the numerator is equal to the degree in the denominator. Now, guys, this is hard. The equation for the horizontal asymptote will be the leading coefficient in the numerator over the leading coefficient in the denominator, guys. Ooh, what in the world am I talking about? The leading coefficient is the number in front of the term with the highest power. Let me say that again. The leading coefficient, guys, is the number in front of the term with the highest power, okay? That's what I mean by the leading coefficient, okay? So you got to take the leading coefficient in the numerator over the leading coefficient in the denominator. Let me do a quick example for you. Example 1. Let's say I have f of x is equal to 2x over 3x minus 1. I want to find the horizontal asymptote. The degree in the numerator is 1. The degree in the denominator is 1. They're equal to each other. So then, guys, my horizontal asymptote is going to be the leading coefficient in the numerator, 2, over the leading coefficient in the denominator. So my equation would be 2 over 3. In other words, when I graph this function right here, I'm going to go to y equals to 2/3, which is about here. And I am going to have a horizontal asymptote right here at y equals to 2/3. By the way, guys, there's a vertical asymptote on this one too. What's the vertical asymptote? Can anybody tell me? Ooh. Ooh. Nobody? Come on, somebody. Drop it in the chat or something. What's the horizontal asymptote, guys? I mean, not horizontal, vertical asymptote. Come on, guys. You mean nobody knows? Oh.
Just give me a minute.
Give you a minute.
-3?
No, not -3. How do you find vertical asymptote?
I don't know.
Come on, it's in your notes. Hint.
3x equals 1/3.
Yes, lady, 1/3. You take your denominator, 3x minus 1 equals 0, and solve it. So yes, you have a vertical asymptote at 1/3. So then you would go over here, guys, and plot out your vertical asymptote at x equals to 1/3. Yeah, okay. And then if you're typing this on a graphing calculator, you have to enclose the denominator inside a set of parentheses, okay? And if you go on the table, guys, you will see, on the graph, you will see where the graph breaks off around x equals to 1/3. And it flat lines around y equals to 2/3. Okay, so let's do another one. So guys, here's another one. And this one right here, I have, let me see here. F of x is equal to 3x over x minus 3. So the degree in the numerator is 1. The degree in the denominator is also 1. So now I'm going to take the leading coefficient in the numerator, which is 3. The leading coefficient in the denominator, which is 1. So the horizontal asymptote would be 3 over 1, which simplifies to y equals to 3. Okay, so that's the second case for these problems, guys. And so let me go ahead and do the third case. And the third case, case number 3, is where the degree in the numerator, guys, is greater than the degree in the denominator. And guys, you'll love this one because there's no horizontal asymptote. When the degree in the numerator is greater than the degree in the denominator, no horizontal asymptotes. All right, by the way, this is also where we encounter the oblique asymptote. How does the oblique asymptote come about? This is how you find your oblique asymptotes. Guys, this is not on the test. This is not on the assignments. If you find one of these on the assignment, let me know so I can go ahead and get rid of it, okay? On this one right here, we're gonna save it for pre-calculus, but I just wanna mention it, okay? In the case of this problem, guys, the degree in the numerator is 2. The degree in the denominator is 1. So there's no horizontal asymptote, but this one will have an oblique asymptote. You get an oblique asymptote when the degree in the numerator is exactly one more than the degree in the denominator. One more. So in the numerator, the degree is 2, and the denominator it's 1. 2 is exactly 1 more than the denominator, so you're going to have a oblique asymptote, oblique or slanted or diagonal asymptote. Now, how do you come up with the oblique asymptote? By the way, it's a diagonal line, so it's going to be a slope line. How do you figure it out, guys? I'm not going to do it, but I'm going to show you. You would take the denominator of the fraction, divide it into the numerator, and that will lead you to your oblique asymptote. But we're not doing oblique asymptotes in this class, okay? We're leaving that for pre-calculus people. So those are the cases for the horizontal asymptote, guys. So now we're going to find the intercepts, and then we'll go ahead and consolidate all this information together and graph these rational functions. Okay, step 4, guys. Yeah, I know, all this time, only step 4. Okay, we're finding the intercepts. Finding the intercepts. What intercepts? The X and the Y intercepts. Now, to find the Y-intercept, that's easy. You just go ahead and find f of 0. That's easy, okay? Now, it's the X-intercept you have to worry about. And to find the X-intercepts, guys, you simply do this. Set the numerator equal to 0 and solve. Set the numerator equal to 0 and solve. So what in the world am I talking about? Let me go ahead and give you guys a quick example. Let's say I have x plus 2 over, whoops, Shazam. Okay, I didn't mean that. X plus 2 over x minus 4. Now, guys, you know what? Let me ask you some further questions too. I'm not just going to ask you to find the Y-intercept and the X-intercept, but let's go ahead and start with that. The Y-intercept. How do we find the Y-intercept? Plug in 0 for every x. So 0 plus 2 over 0 minus 4 gives you 2 over negative 4, which reduces to negative 1/2. So the Y-intercept for this one is at 0, comma, negative 1/2. Now, we need to find also the X-intercept. To find the X-intercept, we take the numerator, set it equal to 0 and solve. So if you take x plus 2, set it equal to 0 and solve, what do you end up with? X equals to negative 2. So the X-intercept would be at negative 2, comma 0. Bam. Okay, now guys, you ready? What's the vertical asymptote for this one? What's the vertical asymptote, guys? Anybody? Oh, come on, guys, you can do this. I'm gonna help you out. X equals to, you tell me.
4?
Yes, yes, Sylvana got it, and I think somebody else said it too. Very good, 4. What number makes the denominator 0? All right, here's the next question. Does this one have a horizontal asymptote? Does it have a horizontal asymptote? Yes or no?
Yes.
Yes, very good. What is the horizontal asymptote? What is the horizontal asymptote, guys? Come on, we can do this.
Negative 1/2.
Not negative 1/2. Negative 1/2 is the Y-intercept.
1?
1, Sean. Very good. 1. Yes. How do we get the 1? The degrees, guys. The degree in the numerator is 1. The degree in the denominator is also 1. And so when the degree in the numerator is equal to the degree in the denominator, you just take the leading coefficient. 1 over 1 reduces to 1. Yes. All right, guys. So pretty much, guys, that's it. Now, if you want a more precise graph, you're actually going to have to create a table of points so you can get some additional points on the graph so you can come up with a precise graph. So now, guys, we're going to graph one from scratch. Basically, that last problem, we could have graphed it too, but I'm not graphing that one. So we're going to graph now one from scratch. By the way, again, if you have your graphing calculators, guys, this is a piece of cake. All you do is go into the Y editing screen, Y equals 2. You type this in, x plus 1 in parentheses, divided by x squared minus 4 in parentheses and hit graph. Yep, it's that easy. Okay, so let me take these away. So let's analyze this one and we'll go ahead and do a graph, guys. First and foremost, this one does have vertical asymptotes. The vertical asymptotes are those values that make the denominator equal to 0. There are 2 of them, x equals to 2, x equals to -2. Next, horizontal asymptote. Remember, the horizontal asymptote has to do with the degree in the numerator over the degree in the denominator. So on this one, the vertical, Shazam, the degree in the numerator is 1, degree in the denominator is 2. Since the numerator is less than the denominator, the horizontal asymptote is y equals to 0. Aha. Now, X-Intercept, guys, the X-Intercept, take the numerator, set it equal to 0, and solve to get x equals to -1. Bam. All right, guys. The Y-intercept, plug in 0 for every single x to get 1 over -4. So your Y-intercept is at 0, -1/4, and your X-intercept is at -1, 0. Guys, we're ready to start graphing. You ready? I know. We're gonna graph the first one. All right, guys. So here we go. Let's see how we do with this. First, I always like to plot the asymptotes. Now, on this one, we've got a vertical asymptote at x equals to +2. Another one at x equals to -2. Then we've got a horizontal asymptote at y equals to 0. Okay, so there's the asymptotes. Now, we're going to go ahead and plot the intercepts. We've got an x-intercept at -1, 0. Right here, -1, 0. Ooh, somebody should be asking a question. We got a y-intercept at, right here, guys, at 0, -1/4, which is right about here. Now, guys, basically, we just graphed 2 points on this graph. We don't know what's going on with this graph. So this is where the table of points come in for you to find some additional points on the graph. For example, if you wanted to create a table, guys, you could go ahead and plug in values that are in between the 2 vertical asymptote, +2, -2. We already have a value here at x equals to -1, at x equals to 0. What about at x equals to 1? If I take 1 and I plug it into this function, what do I get? 1 + 1 is 2. Guys, remember my space on here is limited, okay? Limited, okay? So I don't have that much space to graph all of this, okay, guys? So if I plug in 1 in here, by the way, whoever has a graphing calculator, plug this into the graphing calculator so we can get some values on this graph because I don't want to keep doing this all night, okay? So anyways, guys, when x is equal to 1, if I take 1, plug it back into the function, in the numerator, 1 + 1 gives me 2. And the denominator, 1 squared is 1, 1 - 4 is -3. So I'm going to get a -2/3 when x is equal to 1, guys. When x is equal to 1, I'm at -2/3, which is right about here, guys. Okay, so I should have a general direction of which way the graph is going in the middle. But what about in the right, guys, on the right side? What about on the left side? On the right side of this vertical asymptote, on the left side of this vertical asymptote, what's happening? So guys, yeah, we need to plug in some additional values. For example, when x is 3, 3 + 1 is 4, 3 squared is 9, 9 - 4 gives you 5. So that's gonna be 4/5. Now, when x is 3, the graph is located at 4/5. 4/5 is just before 1, so you write about here. The thing about these graphs is that they have some sort of symmetry, guys. So if we graph this piece over here, remembering that the graph approaches the asymptotes, but it doesn't quite get there, okay? So this graph right here is going to reflect and come over here, guys, in this corner over here to mimic this piece right here, okay? So that's that. Now, in the middle, we need to figure out what's going on over here. If I were to put in, let's say, I don't know, over here at -1.5, what would happen, guys? what would happen? It would go into the positive area over here somewhere. So in the middle region, this is what the graph is going to look like. It's going to get closer and closer to the vertical asymptotes, but never quite getting to those vertical asymptotes. So this is what the final graph will look like, guys. Now, I know this is a little rough. Yes, it's supposed to be looking rough because I am doing this on paper, guys. But let me tell you something. If I do this on the calculator, it's going to look so much better. And I am going to be doing it on the calculator very shortly with you, okay? So just give it a little bit of time, and then we'll go ahead and do it on the graphing calculator. All right, guys. So do you feel like I need to do another example, or should we just end it here and then go ahead and move on to the problems on the computer on my math lab? Because there is a word problem on there that I need to highlight. What do you guys think? Okay, sounds like you guys are done, like you're overwhelmed. That was a lot. Yes, okay. I am going to get to the calculator and graph some of these with you guys, okay? So I am going to pause the video here, guys, and then we'll